So in this video, we're just going to go through a brief introduction to organic chemistry. This is a vast area of chemistry, so we're just going to start with the basics and build up from there. Obviously, you'll be aware there are drugs, vitamins, plastics, a lot of our fibres, as well as carbohydrates and protein, and the chemistry of life is all based around carbon. So it is a significant topic to start. So we consider organic compounds to be those containing carbon along with one or more other elements. And those other elements are normally hydrogen, oxygen, nitrogen, sulfur, or halogens. But others can be in organic molecules as well. One of the most important class of organic compounds are, of course, the hydrocarbons, which you may have studied at GCSE. As their name suggests, they contain only hydrogen and carbon atoms, so you may think you're quite limited there, but for reasons we'll see later on, you can have many, many different hydrocarbons. And in fact, crude oil is made up of hydrocarbons and is one of the world's most important raw materials. So what makes carbon so special that it's able to form all these different molecules? Well, it all comes down to the place in the periodic table. And I'm sure you can see that carbon is there in the middle of the second row of the periodic table. So carbon's got quite a small atomic diameter and also has a tendency to form multiple bonds. When you also look at electronegativity values, the periodic table shown there shows electronegativity values, and you can see carbon's got a value of 2.5, which is a pretty average kind of value. And so carbon bonds with other elements tend to be non-polar or only have a small polarity, and therefore carbon forms very stable covalent bonds. And also when we come to consider carbon and hydrogen, you can see the values for carbon and hydrogen are very similar as well, 2.1 and 2.5. So again, those carbon-hydrogen bonds have very little polarity and are very strongly covalent. You can also see when we look at bond enthalpies on the right-hand side here, that the carbon-carbon bonds are strong as well. So a carbon-carbon bond has a bond strength of 346 kilojoules per mole. And where you compare that against the bonds of between two of the other elements, so you can see that is actually very strong. The only stronger one in terms of single bonds is going to be hydrogen at 436. Obviously, hydrogen couldn't form a large network because it can only form one bond, whereas carbon can form 4 bonds. So this behaviour results in carbon being able to form many, many different types of hydrocarbon. And you can see some examples here. We've got a chain on the left-hand side up here. Carbon can also form ring structures with double bonds, ring structures with single bonds, and can also have triple bonds there as well. And these structures can get extremely complex, as you can see there. But what our job will be is to break down even these very complicated molecules so that we can understand some of their chemistry. So in order to start making sense and trying to make organic chemistry a little bit more logical for us, we need some definitions. So the first one is a homologous series. This series contains similar compounds in which adjacent members differ by the formula CH2. So they have similar chemical properties and just a slow change of physical properties like melting point. And one series I've shown you there, this is the alkane series, and we start here with methane, which is the first one of CH4. The second one of ethane, we've added a carbon and we've added 2 hydrogens there, so they differ by CH2 as we go through. So those first 4 members there. The third one is propane and fourth one is butane. And coming up with ideas and recognising such things allows us to start putting organic chemistry on a more logical footing for us. And a functional group is the reactive part of the molecule. So the functional group of the molecule is the one that gives that molecule its characteristic reactions. So it can be many things, and we're going to look at some functional groups now. So this handy table shows us some of the functional groups in organic chemistry. Now don't worry, we don't need to go through all of these at A level, and I'll show you the table we need to go through at A level on the next slide or so. So this may appear to be overwhelming, but in fact it helps us a huge amount in organic chemistry. Otherwise we'd have all these millions of compounds and each way behaving in its unique fashion. We wouldn't be able to predict any of the reactions. But by looking at the functional group in the molecule means that we can come to a logical route about how to make it and how it will behave. You'll notice that in these pictures, the letter R, capital R, is used. R just means the rest of the molecule, so it's normally the rest of the carbon chain, or it can also be hydrogen in some cases as well. R, and you've got R1, R2, R1, R2 for this one here, alkyne. That just could be two different R groups with a triple bond in the middle there. So you'll be relieved to see that the ones that we need to know for A level are much fewer than the ones in the table on the previous slide. So these are the ones that we're going to look at. Some of these we won't tackle until we get to A2, but certainly the first few, alkane, alkene, alcohols, haloalkanes, we will be looking at during our AS year. So what we'll do now is we'll just go through a few of the functional groups and look at the series that we have. So the first one are the alkenes, and our first alkene has got two carbon atoms in rather than one. And the reason is, of course, because an alkene, the key feature of that is that it has a carbon-carbon double bond. And you'll be able to see that each of those, the four that I've shown, have got a carbon-carbon double bond in them between two carbon atoms. So we'll move on to the alcohols now. Alcohols have the OH functional group, which you can see here in each of the molecules. And again, each of these differ. I start with one carbon, and as you go to that one, you can see that each one I add a CH2 group to the series as I go through. So our next group are aldehydes. Aldehydes have this functional group. They have a carbon-oxygen, a double bond, and an H. So this is the key feature that they all have. If I just highlight that in yellow, like so, and you can see that in each of these molecules as I go through, and each of them I'm adding a CH2 group. Moving on then to carboxylic acids. Carboxylic acid is the key group that we're looking for on this one, is this C double bond O, OH, like so, and you can see that in each of them as I go through. I start with one carbon, go on to two, and then three, like so. And the final one for this page are nitriles. Nitriles all have a carbon-nitrogen triple bond in them. As you can see, the first one I've got two carbons, and then I go 3, 4. I can't have this one here, so I couldn't have HC triple bond N. That is, of course, hydrogen cyanide gas rather than a nitrile. So next series we'll look at other haloalkanes. These all have a halogen in them attached to a carbon, so they must all contain a carbon halogen double bond. And I've just shown that by an X. Obviously halogen could be any member of group 7. And the first one starts just CH3 and an X, and then I add a CH2 group as I go through. Moving on to ketones now. Ketones all have this group. They've got a carbon, and then they are going to be attached to C double bond O, and then they're going to have another carbon like so. So the smallest one we can have is going to be 3 carbon atoms, which is this one here, and then I just added a CH2 group as I go along the series. Ketones are very similar to aldehydes. Aldehydes we looked at on the previous page, they have C double bond O and an H like so. So if that's the carbon there, the key thing is an aldehyde is you must have an H attached there. We'll move on to amines now. Amines have an NH2 group. These are primary amines. We'll look at amines in more detail when we look at their chemistry, but they all contain a carbon attached to an NH2 group like so. And you can see that in each of them here as I go through, and I add a CH2 group into the series. So these molecules again all would have a very similar chemistry. Now these two get muddled up. So amines you have at the top there, primary amides now. I've included this carbon oxygen double bond there for these. So they have that group here, but with a carbon oxygen double bond attached. And again, we'll do more about these. I've shown you primary amides. The difference when we look into this is you'll notice I've got two hydrogens attached onto the nitrogen there for that one, and for also these there. Obviously, those don't have to be hydrogen atoms. They can be carbon chains as well, but we won't go into those complexities at the moment. And our final one are the acyl halides. These are similar to carboxylic acids in a way, but with the OH replaced by a halogen instead. So again, I've got them there. So they all have this group, which I will just highlight there. You're going to have the C double bond O with an X. And again, as you just go through, you keep adding a CH2 group for series. But they're all closely related. So just before we get into more detail, let's have a look at a few more definitions. An alkyl group is an alkane minus a hydrogen atom. So methyl, which I've shown you there, is going to be a CH3 group attached to another carbon, for example. So it would be carbon, CH3, and attached there. So if I just highlight it on this one, that group there would be a methyl group. And this is going to be handy when we come into naming compounds. And again, this one here, which I will pop in blue, that would be an ethyl group there. An aliphatic compound contains hydrogen and carbon joined together in straight chains, branch chains, and non-aromatic rings. We'll look at that in a minute, what aromatic means. So that would be an example of an aliphatic. An alicyclic is it's just got the same, but they are arranged in a ring of some point, with or without side change. Now, aromatic compounds we will look at when we do A2 chemistry. They have benzene rings. Benzene rings are shown as I've shown there, hexagons. You either have alternating single and double bonds, as I put in that example, or you put a circle in the middle, like so. Don't worry too much about those at the moment. We'll look at those more when we come on to benzene chemistry. And then finally, saturated compounds contain only single carbon-carbon bonds, but unsaturated compounds contain multiple carbon-carbon bonds and aromatic rings. So have a look at these 9 molecules and see if you can tell what functional groups they have, and we'll go through them in a minute. Okay, so let's go through these. So number 1, you have got carbon-carbon-carbon chain, and in the middle C double bond O, so that's a ketone. This is the important part of the molecule for number 2. CnH2, so that's an amine. C double bond O OH means that's an carboxylic acid. And number 4 here means that's an alcohol with a COH. Number 5, C double bond OH is an aldehyde. Number 6, C double bond O NH2 means you've got a carboxylic acid. Number 7, C double bond OH means you've got an aldehyde there. For number 8, you've got a nitrile group there, and you've also got an alcohol group there. And for number 9, finally, we're going to have a carboxylic acid group there, C double bond OH, and here with the carbon joined to an NH2, that's an amine group.